All right, Bart De Smet. It's been a long time, man.
It's been way too long.
Way too long.
Yeah.
So let's start right off the bat. I mean, what have you been up to? I haven't talked to you since early in the Windows 8 time frame.
Like a year and a half or something,
Yeah.
I think, right? I've been up to building distributed event processing systems here based on RX.
Nice.
In the online services division, or application and services group, or what it's been called now, right?
Okay.
And those things are powering Cortana.
Wow.
So it's been a hectic set of months, actually, about a year and a half now. Building that out, focusing on a whole bunch of link-related things, RX-related things, both on the device as well as in the cloud. So it's totally this devices and services
Awesome.
vision all the way through. Yeah.
Excellent. It's really nice to hear that RX is like powering one of our sexiest new features that
Yeah.
we announced at Build.
Exactly.
And it sort of makes sense given the amount of asynchronous stream processing one would need to do.
Yeah.
So, how, just at a high level, how is RX doing its thing in this model?
So effectively, when you go to the phone and you say remind me when I'm near a grocery store or something, that's a good example of like a local RX rule that's been set up on the device. So it will use the sensors of the phone to calculate geofences. It will then effectively do a subscription to the geofence stream, and then have an action manager. So the action is the observer, and the observer will be something like do a toast notification or ring the bell or something, right? And then for like the more advanced scenarios, we have pretty much the same thing, but then in the cloud. So if you go to Cortana and you say I want you to notify me when my flight has landed or my flight is late or something, that will become an RX subscription in the cloud against the world's data stream of, for example, flight information. And that will be things like, flights.where the flight ID equals BA9049 or something, typical example we use. And then, do things like, select into a toast notification and subscribe to Azure Notification Hub or something that can deliver notification onto the device. And that is also rules that stretch both the device and the cloud. So the way to think about it is that a subsystem of Cortana in the cloud is actually responsible to formulate all those intelligent queries that can span both the device and the cloud. So a good example is traffic notifications. Like we know from your shadow calendar that you have a meeting on the Redmond campus in an hour or something, and we know that the default travel time is 15 minutes. Now what we will do is we will have a local signal based on the geolocation to know where you are, like half an hour in advance of the meeting, for example. And then we can calculate, based on traffic conditions that come from the cloud, we can actually calculate how long it will take for you to get there. So we can remind you to go to your meeting 20 minutes in advance as opposed to 15 because traffic conditions are bad, or because you're in a different place than where we expect you to be. So those are typical rules that are completely expressed using RX. Things like project traffic conditions onto timers, and then fire timers when the user has to leave, subscribe that thing to a toast notification, that kind of stuff. But like spanning both the device for local geolocation as well as the cloud for ongoing streams of data about traffic on I-90 is bad and those kind of things.
Interesting. I mean, if you think about like back in the day when we first talked about RX, it's really about orchestration, right? And so now that you brought RX into the cloud, how has that changed, or has it changed any of the architecture or design of RX itself when running in this giant distributed system interacting with random client devices?
Exactly, yeah, there's a couple of changes, but I would say none of them are fundamental.
Cool.
Like the fundamental concept of having observables, which are lazy, meaning they don't do anything until you subscribe to them, and having observers, which are the sinks, the places where you notify to, that's completely the same. Now, a couple of things you have to do, like to sort of adapt to the reality of the cloud, of course, come in. And that makes the API look slightly different, but in principle it's the same as what we already have. So observables, query operators, which are like parameterized observables, if you will, the notion of subscriptions, the notion of observers, notion of subjects, those kind of things are all the same. Now, to decompose the problem, you can really start thinking about, if you're in the cloud, how do you deal with reliability? That's like one thing. Like you have all of those computations sitting on a whole bunch of worker roles in the cloud. What if one of those machines goes down? Like how do you recover your computation? Because certain operators are stateful. Like think about the take operator, right? If you do, give me the last 5 or the next 5 events for a certain sports team, winning a match. Well, if you do take 5, you need to have a counter somewhere, right? Like that comes down from 5 to 4 to 3 all the way to 0. Like if the machine dies in the middle and we recover onto a different machine, then we better don't send another 5 messages. We want to sort of only get 2 more messages because we already seen 3 of them. So we need to have a way of persisting the runtime state of query operators. And the way we do that, there's different approaches to that, is checkpointing. So we can actually store the state of the running computation and actually replicate it to different machines, so that when we fail over to a different machine, we come back to the state we were already in to begin with. Now there's different approaches to doing that. Now we can talk a little bit more about that as well, but there's other things we have to deal with as well. So like we have the reliability, that's one thing. The second thing is really all about how do you talk about artifacts? Like how do you talk about a subscription? Now, the way to really think about it is if you look at our Access library, a whole bunch of the concepts have sort of been compactified. Like now I'm getting into some kind of passion after hours of myself. It's like reading books on string theory, where you say like, oh, the world exists not of 3 spatial dimensions, but 10 or 26 or whatever, right? Like, but where are those other dimensions? Well, you don't see them because they're super compact and they're curled up. Now, in Rx that's the case. Like you have a whole bunch of things that sort of the environment gives you, and you don't think about. So those are dimensions that become visible once you go to the cloud. So a good example is the convenience of variables in local process. Like if you do a subscription, for example, you say, I have a source access, I subscribe with an observer, and I get a subscription object. Now at that point, if it's a single process, the only thing you have to do to dispose a subscription is hold on to that object. And you assign it in a local variable, you give it some name. Now as soon as you go to the cloud, of course, and your phone is loosely connected, and you set up some subscription today, and you want to cancel it 20 days from now, no way that object is still going to be in the memory of your phone, right? Even more so, the object is not an object locally, it's an object backing something in the cloud. So you need to give that thing an identity. And local variables don't cut it, of course. Like, you can go down at any point in time. So you need to have a scheme of basically making the identity that you have associated with objects in memory, like just pointers or object references in managed code, you need to make those things explicit. So long story short, people have to supply names to a set of APIs. Like subscribe in the cloud means doing a subscribe, not just giving the observer, but also giving a name to identify the subscription. And then later you can come back and say, I want to get my subscription back, and I want to dispose it. So you have just to remember the name and store it somewhere, as opposed to keeping track of an object that may, be lost when your process goes down.
Sure.
So it's all about like the naming scheme. And of course, like locally, if you really think about it, it's like the way you do things in memory, it's like you do something like var x equals subscribe. Now if you take that x and you move it as a parameter, like it's sort of again like moving arrows, like as we do for all the things in Rx, it's sort of putting things upside down. Now the distributed part sort of adds one more thing, of course, is like Rx is about asynchronous computation, but like if you do things locally, the asynchrony is really the asynchrony of the observer receiving the messages, right? Like you subscribe and you don't get the messages straight away, or you don't block for the messages to come back. But the subscribe itself is an asynchronous operation as well when you do things in the cloud, because your phone connects to a server, and the server can connect to yet another backend server, and there may be many network hops that can all go wrong and may have some latency. So as opposed to having subscribe, you end up with something like subscribe async. Now that's completely isomorphic to subscribe, of course, but like things start to become more and more sort of aligned with the reality of the network and the reliability model of the whole cloud, really.
Awesome. Now, just out of curiosity, how is this related to sort of the work that was done in Eric's team before the great Eric Meyer left?
Mm-hmm. Yep.
The last time I talked to you, you were on his team.
Yep.
Hi, Eric. How is this related to sort of like actors?
Yeah.
Like, aren't actors a good way to deal with the maintenance of objects in a distributed system?
Sure, yeah.
As you had mentioned. So are you using any models from sort of the actor model?
We've looked at the actor model
Okay.
for implementations. In this particular case, we've just gone for a straight approach, like not using the actor model, but we have done prototypes where actually operators are represented as actors. And then you have basically the stuff that the Orleans folks have done, for example, is a very good fit where you can do event stream processing using our abstractions and sort of represent all of the individual computations of operators as effectively actors.
Yeah.
There's a whole bunch of ways of actually sort of skinning the cat, right? And like that's one way. It's a way where you have a lot of fine-grained operations going on between the different actors, like all the messages. We have an approach where, like, you can sort of think of the whole system as being like, a bunch of, little actors stitched together locally. Like, query operators sort of stay together closely. But like, as we scale out across many layers and scale out the computation itself, then the actor model becomes a very, very good fit as well. Right now the queries are kind of, condensed and kind of small. And the approach of like doing checkpointing or continuous state replication, like all of those things fit very well in those models, really.
Can you talk a little bit about checkpointing, because that's new?
Yeah, that's new. Yes. Yeah. So maybe one day we'll actually have that back in the RX code base.
Okay.
But the way to think about it is like if you think about subscribe in RX, like the subscribe method on observable, it's doing a little bit too much. Like it's a whole set of operations it does at the same time. It connects the observer to the source. That's one thing it does, and secondly, it starts the computation. So you end up with an interesting set of race conditions in a lot of cases. And if you look in the RX code, you have something called single assignment disposable, which is doing stuff to make sure that you can dispose something before you have it. Like it's like a future in some sense. Now, why am I bringing that up, right? Like, like what does that have to do with checkpointing? But the realization is like if you subscribe and you get an object back, the object you get back is an iDisposable in RX. But the iDisposable has some immense power. It can actually trace through the whole computation all the way into the schedulers to cancel stuff. Now, if you think about it, that's the same thing you need to traverse all the operators to collect their state. So to save state, like, if we only didn't have a disposable, but we had something more general, then we could use that thing to basically trace through the computation and inform all the components to save their state or to reload their state. So that's basically what we've done. We've sort of taken RX and we've sort of added another layer of indirection in the subscription lifetime or the subscription cycle. So as opposed to subscribing, well, we still call it subscribe actually, but like it's a different interface. When you call subscribe, you get a nice subscription object back. And the subscription object is something you can visit. And then you can have many different visitors that go to that subscription tree and do stuff. So for example, in the cloud, a good example is schedulers. Like schedulers in RX are explicitly parameterized. But if the poor guy in the cloud building, a query, wants to upload that thing to the cloud, like they don't know which scheduler to pick. Like how can they know that they need to use a new thread here, a new thread there, a thread pool here, whatever. Like it doesn't make sense because we need to control the environment and sort of provide the whole hosting platform. And think locally about resources as opposed to fine-grained and let users specify that. So with that visitor approach we can do much more interesting things. Like one thing we can do is distribute the scheduler to all the components. Another thing we can do is distribute the logging component to all the operators so that they can log bad conditions or whatever. And we can go to the whole operator tree to collect state and save it to disk. We can go to the whole operator tree and rehydrate state. So for example, if you have access take5.subscribe something, like the subscription object that you have, first we would call start on it to kick it off. But then periodically at a later point in time, we'll actually go through that thing and say save your state. So we'll walk through the whole tree and say like, oh, take. And take will say, well, oh, I have 3 messages left. So that thing is going to drop 3 into a state writer. And then it's going to traverse into access. And access may be something that subscribes to the traffic stream. And maybe it contains a route ID or like kind of an identifier it got back from an external service. That if you recover it onto a different machine, you need to have that same identifier that you can give back to the external service to say, oh, by the way, I've woken up on a different machine, you need to call me over here now. So that's also part of the checkpoint state. So what we've really done is like taken the RX implementation and sort of teased apart the concerns of like subscribe causing things to be kicked off, and we sort of introduced the delay there. You subscribe and then you have to start it. And that object that you get back, the subscription, is also the one that you use to dispose the computation. It's called stop now. So it's a very natural progression of something, again, which had to do with compactification. Like in RX, the subscribe and the dispose were kind of compactified. They had a hidden visitor mechanism in it, which is simply composite disposables and all of that stuff, which is really visiting a whole bunch of objects as an object tree. So we made that whole concept kind of the bread and butter of it. And that makes it very extensible. Like for example, if a machine goes down intentionally and we have to stop a machine, we want to unload a whole bunch of resources that those operators rely on. But we don't want to dispose, because dispose means stop the computation altogether. It's like if you dispose to, say, a traffic service, you reach all the way to the traffic service and you will talk to the external service saying, stop giving me messages, I'm no longer interested, the user has disposed me. While as if you're unloading the system, because you're bringing it up on a different node in the cloud, in that case you don't want to do the dispose, because dispose is a user intentional thing to get rid of a subscription. In that case you want to go through the tree and say, we don't need you anymore, you can start disconnecting from an external service, which is different from disposing external resources. So like we could easily say at that point, well, the only thing we need to do is all the operators that need to participate in unloading need to implement an additional interface. They are no longer just iDisposable, they're also iUnloadable. They're also iCheckpointable. You know, they're iThis, iThat, and iThe other thing. And then the hosting platform is responsible to basically communicate those messages, those calls through a visitor pattern through the whole operator tree. Nice. And that's really the way that we deal with those kind of things, is like effectively abstracting RX one little bit more, and in a way that you can get back to the original RX model completely. Because something like subscribing and starting is the same as the RX subscribe. And subscribing and stopping is the same as doing dispose. It's just like function composition. Like today we have 2 steps to do that, but you can always compose it back into the good old subscribe if you don't care about any of the checkpointing stuff, for example, or any of the unload capabilities, or scheduler communication capabilities, like, or communicating a logger, or you name it, right? Like it's even extensible to the point that you can say, oh, I have a custom operator, and that operator needs some additional initialization phase or something. Or it's an operator you can sort of pulse periodically to go to the operator and sort of knock on its door and say, like, make sure that you're still running, or make sure that everything is healthy. Or something you can use to do debugging. Like, you know, debugging is something you can do with the same thing as well. You can have, you know, an iDebug view that you can basically go to the subscription and say, give me all your runtime state.
Cool.
Without attaching a debugger, of course, which you never want to do in the cloud, but you can still take out all of the runtime state to see what's going on. And so you can, you know, visit that thing to do things like toString on steroids. You can do like, you know, every operator you could ask it like, you know, what's the size of memory that you're using, so that for every subscription you can see like, oh, that guy is going out of control versus the other guy. Like that guy we need to throttle, or we need to shut down, or we need to alert the user that his or her subscription is like taking too much cloud resources. So it's really an extensible mechanism that doesn't harm the abstractions of RX at all. It's all compositional, you can continue composing operators, but you gain a whole bunch more things where operators can decide to cooperate and sort of like implement additional things, and we just make the way of visiting the operators kind of a general purpose thing, as opposed to something glued into Rx. Like, you know, it was always only about disposing, while as it's a gold mine. You know, that like the operator tree is something you can use for so many other things than just disposing it.
Excellent. And you are.
And we are, yeah. Like,
that's awesome, in a very big way.
Pretty much every other week, you know, we find another reason to add, like, you know, an interface to certain operators, and that's typically the leaf nodes of the computation, the things that talk to external services. A good example is if an external service needs like tokens, authentication tokens to an external, to the other service, and those periodically expire. Like, maybe you need cooperation from the host to do that. Well, you can actually initialize the whole subscription with an authentication provider without you having access to that object, because that object is just an anonymous object. It's been created somewhere, maybe it's contained in a where operator, in a select, and so forth. It's not reachable by any sane means, right? Unless it's parameterized by a whole bunch of things, but those are parameters that the user can't provide. It's parameters that the infrastructure has to provide. So you want to have a way of communicating that global state without, God forbid, making it statics, right, or anything like that. So, so like plenty of examples really to use that.
Cool. Well, after you have your sip, it's whiteboard time.
We should do some whiteboard.
So the last time we had you on the whiteboard, it was a rather incredible diagram where you were trying to explain and successfully explaining where IQbservable fits into this.
And
RX
this is all IQbservable.
See, so that's really, really interesting. So it's sort of the return of IQbservable.
It is, and it's the cool return of IQbservable. Yes, it is.
IQbservable.
Yep.
And you stuck with that name.
We stuck with that name.
Right on.
We just added an additional word in it because we needed to disambiguate with the one we have in Rx.
Sure.
Because we have slightly different signatures here and there, so it's called iReactiveCobservable. Just additional name there. But we still have queues everywhere, like, you know, and we actually have kub servers now too, and subscriptions. I'm not joking. Like, you have subscriptions and subscriptions. So like,
You hear that, Eric, man? I know Eric's watching because I'm going to tell him about this, and he certainly will. It's really wonderful to see, you know, RX at this level of production from Microsoft.
Yes, yeah.
We've seen it, you know, a lot out in the real world in banks and things like that. Really nice to see powering Cortana to this level. Let's rock and roll, man.
Definitely.
All right, let's whiteboard.
Let's do some whiteboarding.
All right.
So actually, let's get back to the thing we mentioned just a moment ago, which was the compactification of dimensions, right? So like, you know, it's this whole, it's starting to be a little bit theoretical here.
That's fine, we like that.
So let's just refresh. It's been too long, exactly. So let's refresh our mind on the 4 quadrants of data processing. And in fact, we had like an additional axis over here as well. We had what I call the data acquisition model. So data acquisition. And that can be push or pull, right? And then we have over here the representation. How do you represent your computation? Do you represent your computation as in-memory objects? Let's just say object-oriented / if we go for .NET-IL code, that could be assembler or whatever. Or do we go with code as data? Like, so this is really code, and this is like code as data. And here we're talking about expression trees, or quotations in Lisp, or any kind of thing. So those are the 4 quadrants we have, and then we can sort of like fill in the interfaces. We know pull-based using code, it's linked to objects, so there we have IEnumerable of t, obviously. We have push-based in memory, that's linked to events and Rx, called IObservable of t. Then we have pull-based using expression trees, like linked to SQL, for example, that uses IQueryable of t. And then we have push-based using expression trees, and that's where our funny guy comes in, IQbservable, right? So that's this one over here, IQbservable of t. Okay? So those are the four interfaces we have here. Now, the question is like, is that sufficient? In reality, if you do everything in the same process, that's far from sufficient. Oh, it's far sufficient, not far from sufficient. Now, as soon as you start doing remoting boundaries, you end up with a couple of interesting additional things here. Now, the additional dimension we had here, let's actually, just for clarity, add that one over here as well, was the scheduler, which was about where you execute stuff. Okay, so that's sort of like, this also is the one that gives you the time dimension, by the way, because it maintains the clock.
Okay.
Right? So, so that's really all about coordinates, really, like, you know, where you do it, is it on a thread pool or on a new thread, and when you do it, right? Now, if we look at this, we can really sort of think about this thing as having a whole bunch of curled up dimensions over here as well. That, like, if you do things in a local process, you know, everything is kind of totally fine. You can say, I have, you know, traffic, for example, which is an IQbservable, and on traffic I do where, you know, t goes to t.dot equals I90 or something, and then on top of that I want to do a subscribe, right? And let me leave a little bit of space here.
Okay.
So let's actually do it in two steps. Let me actually write this whole thing as, you know, res for results, right? And that thing will be, you know, an IQbservable, let me just abbreviate IQ, of traffic info TI, okay? And this thing, obviously, traffic is also an IQbservable of TI, simple. Now, with this thing I can do res.subscribe and pass in an observer over here. Now here's the first thing. What's the type of the observer in Rx? It's actually an IObserver of traffic info. Now what does that mean? That means that I'm subscribing to something that's completely represented using expression trees, like traffic and where and a lambda expression and the whole shebang. But I'm subscribing with a local observer. So if you think about this, this thing may be running in the cloud, and you have an expression representation of that, so you can serialize it and send it into the cloud, but you have a local observer here. So there's something kind of fishy about it, because now you end up in this situation where you have traffic over here in the cloud, and you have your where class in the cloud, and now somehow you have the phone here, that's a Windows phone, and this thing has an observer sticking out of it. IObserver IV of T. And now you have data communication here. So you have a local observer on the phone that's observing things from the cloud. Now, that's good, but this thing is loosely connected.
True.
Like, so this is not the best thing. And secondly, well, when your phone goes down and you restart it and then it starts up again, or your battery goes flat, well, that connection needs to be reestablished. So this is a little bit doing too much at the same time. You sort of want to keep this whole computation in the cloud and say, I want to create a subscription in the cloud that has traffic and where, and I want to subscribe to that thing, say for example an Azure push notification observer that's sitting over here. So I want to be able to remote into the cloud, I want to be able to remote into here something that has over here an Azure notification hub observer.
Okay.
Okay? And that Azure Notification Hub observer, when messages arrive, it will go to the Azure cloud over here, and that one is responsible to put things onto the device. Now, everything I have here is a standing query that I'm just parking in our data center somewhere. It's sitting there and it's running forever. So, what do we need to do to enable that? Well, this observer over here, it's not good enough. Because this observer is something that's a local object, and we want a remote observer in the cloud. So we had to change that to have an IQbserver. Like have an observer that has an expression representation associated with it. Now, we actually play an interesting trick here. How do we know which observer that is? Like, you know, with an expression tree, well, you can do something. You can just represent some code as data. But like, what's the identity of that guy? So, if you look at this whole thing, we have two unknowns here. We have traffic that I'm pulling out of thin air, and the observer. So what we have is an abstraction around this whole cloud, and an abstraction around the phone that's exactly the same, and we call that thing IRP, which stands for I-reactive processing. And I-reactive processing, the first order approximation is like link to SQL's data context. If you have link to SQL in a data context, you can walk up to the data context and say, get me a table. And when you call get table, you give it a name, and you get an IQbservable back that you can write a query over. Now this thing is the same thing, where you can walk up to the cloud and say, get me the observable with identifier traffic. Get me the observer with identifier Azure Notification Hub. And then you have two local proxy objects in your process. So you get like, a little proxy to traffic, you get a little proxy to Azure Notification Hub. You compose your query over here. So you build up a local object graph that contains where and traffic and Azure Notification Hub. And then at some point you say, now upload this whole computation into the cloud. So when you do something like context, which is an instance of IRP for the cloud, like data context, and you do get observable of traffic info, and you pass in here traffic, the identifier. In reality it's a URI, just to have some more structure to the string. But what you get back here is an I-reactive observable of traffic info. And that's traffic. And that's a local object. Get observable doesn't go to the cloud, it just creates a local proxy to an object. Now, what's the expression tree representation of that guy? That's where the fun comes in. The expression tree representation of this guy is simply a parameter expression that as the name of the parameter has traffic. So it's an unbound parameter. So as you compose a whole bunch of queries on top of that thing, you have an expression tree that will contain an unbound parameter called traffic. And when we upload that to the cloud, there is a binding process that will check a registry whether it knows about traffic, and it will bind it to the concrete instance. So the whole expression that goes to the cloud is really just an unbound expression in some kind of scope that's represented by that cloud. Okay? Now, even where, funny enough, the where operator here, we just use one more color here, the where operator is nothing fancy either. The where operator, if you think about it, what's where? It's an observable that's parameterized on another observable and parameterized on a predicate. So this thing, the where operator, is really just shorthand syntax for the following. Where is the same thing as doing context, get observable, let me do get obs, of traffic info, get observable of IObservable of traffic info, comma, an expression tree that contains a function from traffic info to Boolean, and that returns a traffic info observable. And that thing has a name too, it has the name where. In reality it's a URI, it's something like Rx operators where. But like it becomes an invocation expression of a function that's called where, that then is applied to the traffic and gets in this particular parameter.
Nice.
The only thing is that the where method is a method that just has on top of it some attribute saying known resource, and that thing has that URI in it. So the user could be very masochistic and write everything using get observable. You could do get observable of the where operator with two parameters and get the select operator and do a whole bunch of function applications. But you can simply map all of those things as .NET artifacts with an attribute on top of it. To the extent that traffic can just be a property on a class where you put an attribute on top of it saying known resource of traffic. So you can expose all of your artifacts using very easy to use .NET methods. Now the same for the geeobserver over here. The geeobserver is just retrieved by doing context.getObserver of whatever this thing is, Azure Notification Hub or something. So you compose that whole thing over here, and then you have to upload it to the cloud. Now, how does it upload to the cloud? Well, that's where this guy comes in, the subscribe method, of course. Now, if you have this thing here in the cloud, and locally you will end up with an IDisposable D, we've already talked about this being not very reliable. That's a local object. You want to be able to get your local proxy to that subscription back at any point in time in the future.
Okay.
So we need to have a way of giving this thing a name that will be mapped onto a unique identity in the cloud that's partitioned by partners, so that, like, you know, you can have a subscription called traffic and I can have a subscription called traffic or whatever, like, you know. So there's a whole bunch of like ceremony around it to isolate different users, of course. But the high level thing here is you want to give this thing a name. So the subscribe method over here, well, just taking in the observer is not sufficient. We need to give it a name as well. And so I'll give this thing, you know, Bart's traffic or something. Bart traffic. Here we go. Like that. But this is a network call. This is a network call going to the remote system. So subscribe is kind of cheating here. Like, because this network call could fail, could be long latency. So this thing needs to become subscribe async. And then the thing you get back over here is actually a task, of course, so you can await the task. And the thing you get back is not an IDisposable, but it's, guess what? An IQbscription. IQbscription.
Of course.
Now, what's the subscription? We're a one-trick pony in this whole world. The subscription is a subscription represented using an expression tree. What's the expression tree going to be here? It's just going to be a parameter expression containing the name Bart traffic. Now, on that subscription, what you have here, let me call it S, you have a method called dispose. It's a network call, so it's dispose async. And what does dispose async do? It serializes the expression tree which contains this name into the cloud, so it gets bound to this object tree, and then we can visit that object tree to say, dispose yourself. So everything is the same, like, you know, observables, observers, subjects, and subscriptions all have an explicit identity that is, you know, accessible using remote proxies. So you have async everywhere, and that's represented using expression trees. So if you look at those curled up dimensions that I was talking about here, really what's sticking out of this, like, you know, if you now zoom into this thing, you know, you have a dimension, set of dimensions here that we didn't see before, which is about naming and identities, which of course in memory is just the garbage collector, the .NET memory manager, or whatever, you know, your allocator is giving an identity to your object by simply allocating a memory address for it. And the names then that you associate with those identities are local variable names. Like you say, like IQbservable res equals something. Res is your name. But now in the cloud you need that name to be distributed. Like, many people need to know about that identity or about that name association with that particular identity. So naming is explicit. And the second thing here is the asynchronous behavior is also something that was curled up, where in the local process you can say, well, subscribe, you know, itself is kind of asynchronous because we have the observer. And we can notify the observer about an error at any point in time. But what if subscribe fails in the cloud and you're not allowed to do a subscription? Authentication problem. Well, then we can't use the argument of, like, we're going to tell you about the authentication problem by doing observer on error. Because you're not authorized to even do an on error. So we can't go to Azure Notification Hub to communicate an error to you. Like, this thing has to throw asynchronously. So we need subscribe async here to accommodate for, or to basically align with the reality of this thing, go into the cloud and be able to fail long way before that object tree is actually being configured. Like, maybe we can't even set it up, like, you know, if over here I'm doing traffic equals get observable of foo, and foo is unbound, and the cloud doesn't know about foo, then it's only the server that's going to figure out I can't instantiate this computation. Hence, I can't instantiate a way of actually communicating to you the error, because I can't resolve the observer. So we have to fail in some other way. So we need the subscribe, and we make the subscribe async because it's a remote call. So that's really like, the 2 dimensions that were sort of curled up. There's in fact like one more that's actually curled up.
I'm sure there is.
And the one more has to do with reliability.
That's an important one.
Exactly. So if you have communication between different systems, you need to be able to actually replay messages if you go down, as long as you have a checkpoint at your state. So let's just draw a little. Oops, I didn't bring a wiper here. Let's just squeeze it in somewhere. Right?
Okay.
Over here. Say that you have what we call a QE. That's a query evaluator. That's like the engine in the cloud on a worker role that runs Rx. Like this variant of Rx that, as we've seen, is completely isomorphic to regular Rx. Now, this QE, inside of it, it may have a long computation here. That's stateful. Like, say a take operator and, whatever, right? Like combined latest has values of the left and the right hand side, the latest values, stateful computation. So we need to be able to save this state. Now we already talked about like how in the engine we use an abstraction that's similar to this one, but that allows us to visit that object tree to collect all the states. So it's like an IQbscription, but it's really an I subscription. Because at some point you shake off the expression trees, right? You have the world of expression trees here, but if time comes to execute it, you need to descend to this plane. So you need to get rid of all the queues, right? IQbservable becomes IObservable, IQobserver becomes IObserver, IQubject becomes ISubject, and ISubscription or Qubscription becomes subscription. Like it's completely isomorphic. One is expression trees, the other one has gotten rid of them. So like post the binding phase in the cloud and all of that stuff, all the queues go away. So now you end up in this space over here. Now this is a slightly different space we have there because we need to have subscription objects that you can visit. So it's not IObservable, it's what we call ISubscribable of T, which is really the same as IObservable with just that delayed effect of you subscribe and then you have to start. And you can also visit that subscription to do checkpointing, those kind of things. So that's the ISubscribable interface. Now we have that thing over here now. So we can visit this tree to say like, save your state. And then this guy may say like, my state is 3, my state is some identifier, whatever, right? So we can persist all of that stuff to disk, and later we can visit that same tree, which we can reconstruct because we know the expression tree. We can recompile it, reconstruct the object tree, and give the state back to it. So it's as if nothing happened, it can reapply the state. Now, the interesting thing is, when you save that state, you're still dependent on the things that come from the external world. Like at some point, a message comes in here, message 1, message 2, message 3, and so on and so forth. And those messages come into the query evaluator and will modify the state here. Now, when you save the state, at that point, you never need those messages anymore. Like, message 1 has come in, and that caused, the counter over here. Say that this thing was a take 5, right? Like if it's take 5 that it's doing. Like originally this value is 5.
Okay.
Message 1 comes into the QE, take goes to 4, right? Like 4 elements left. Number 2 comes into the QE, flows through the graph, and this thing becomes 3 elements left, and so forth.
Sure.
So like things are just moving up. But now say that 3 came in to the engine, and the engine became 2 over here, but we saved the state before that happened. So the state in the store is actually ID and value 3. So we keep adding things here, like 3 came in, 4 came into the engine, and this thing has moved to 1, and now we crash. Now when we recover, we'll see 3 over here, but the effect of message 3 and 2, or like message 3 I believe I was at, like those 2 messages need to be reapplied to the computation to converge back to the original state. Now there's different ways of doing that, like you could say, we're not going to do periodic checkpointing, we're just going to replicate all the state across the data center, so that we sort of have all of that state available all the time on different machines. That's an option, but it's more expensive. The checkpointing approach, like in practice, works very well because a lot of those streams give you data every so often, especially data that affects the computation, because a lot of things is like filtering. Like, when you filter something, like, you just let through a tiny percentage. Like traffic where the road is I-90. Like, traffic may be a huge fire hose of like a lot of data, but like as soon as you're beyond, this stateless filtering and stuff, like, this state doesn't change that often. Like, it just, happens every so often. So checkpointing is kind of, for us right now, at the sweet spot. But like, this thing is not tied to a particular strategy of doing state recovery. But now if you think about this whole thing, the interesting point is, like, you need to have the external system be able to replay values 3 and 4. Because if you crash, with an old state, you need to be able to recover things to get back to the state that you were before. So you need the external system to cooperate. Now, what do you need here? Well, one approach that you can take is like give all those messages sequence IDs, sequence numbers. So like, message, 2 and 1 over here. Message 1 is sequence ID 127, this is 131, 132, and 145. Just needs to monotonically increase, doesn't even have to be adjacent numbers or something. It just increases. Unique, exactly. So as soon as you have unique numbers here, like, we can talk to that external system to say, you know what, we've seen everything up to this sequence number on. You can start deleting those messages from your storage. So we can acknowledge we've seen everything up to 131, meaning it can trim its state. And then, when messages come in, we simply have to keep the last sequence ID that we've seen on the edge of the input of that particular computation container. So that's really like, how the checkpointing can work, is we keep watermarks of those numbers. And, we let things go into the engine, and this thing doesn't see any sequence IDs at all. The operators, if every operator would need to have to deal with sequence IDs, the wheels come off quickly. Like, think about combine latest. Like, now you have 2 streams that have sequence IDs. You're combining values, and you end up with new sequence IDs. Where do you get your sequence IDs from? Like, you could do a linear combination between the 2 you have, but like, you don't control those domains. So you may not know how big they are, so you can't do that. You could do string concatenation, but then you need a split function. Like, because if you acknowledge a message coming out of combine latest, you need to acknowledge 2 messages from the sources of combine latest. And so before you know, the thing sort of derails. Like, all your operators have to deal with sequence IDs. So you don't want sequence IDs inside the operator implementations to keep everything nice and pure and simple. But on the edge over here, it's like somebody's throwing a message into this kind of thing. Like, you have a pipe over here, and your message is bigger. Your message contains a payload T, and it contains a sequence ID. The T flows through that pipe, it goes into the container, but the sequence ID is sort of like a mosquito sticking on the wall. Like, so the last sequence ID is sort of kept on the edge of that box where we sort of send that data into, right? So that's sort of the way to think about it. Now, what does that mean? That here you have like one more dimension that we didn't talk about, is the dimension of sequence IDs, explicit numbering of sequences. Okay. Now, if you think about it, sequence IDs is pretty much the same thing as the naming scheme that we were talking about here. When you do an onNext async against the cloud, the onNext async takes in the message as well as an identifier. So everything that's really an object that's tangible, that the infrastructure may need to know about, may need to withdraw, or may need to commit to storage or something, needs to have some identifier. And this actually fits hand in glove with the system that we use, namely Azure Service Bus. Cool. Azure Service Bus has sequence IDs on the messages you receive. So this thing is actually called iReliable. Whatever.
iReliable.
Yeah. iReliable observable, iReliable observer, iReliable subscription, iReliable subject. Like, the whole set of things. Now, what's an iReliable subscription? It's pretty much the same as a regular subscription, but if you would zoom in, and I will just reuse this piece of code here, if you would zoom in to a reliable subscription, the subscriber would take in over here the sequence ID you want to start from. additional parameter. And the subscription you get back would be an iReliable subscription over here. And the reliable subscription has a way of visiting the graph to say, I want you to acknowledge everything up to a certain sequence ID. So you basically see that, you know, it's just an additional parameter on something that's otherwise completely isomorphic. And that's the kind of thing we play everywhere throughout this entire stack. Is like we have that same thing called IRP, iReliable, not iReliable, reactive processing. We have that same interface, and last time I counted, I believe we had 7 copies of that. Like one copy is in the async plane with expression trees and with explicit naming.
Okay.
Async reactive observable. That's what you see on the client. Now, once you come into the server, the explicit naming is actually traded for naming that's associated with in-memory objects that are reliably kept. So you have to shake off that dimension. But you may still be talking to external systems, so you don't want to lose the async portion. So then you have the same set of interfaces in the plane of async observable. Then at some later point, you may be ending up on the edge of this query evaluator, where you need to talk to an external system asynchronously, but with sequence IDs, but with no names, for example. So you have iReliable observable, or in fact, like in that case, it may be without expression trees, maybe iReliable observable. So you have like all those combinations in that space here, plus this one, like, you know, 1, 2, 3, and then this dimension is 4 dimensions. Like you have 4 dimensions where every point in that space, every dimension has 2 points. It's either async or it's not async, it's named or it's not named, it's reliable or it's not reliable, or it's expression tree and or not expression tree. Like, you know, you have 16 potential points in that space. Not all of them make sense, of course, but you can have like up to 16 of those interfaces. And really what happens in our infrastructure is every time we switch a layer, we simply translate one interface to the other. But the nice thing is they're isomorphic. Like, you know, going from like async with sequence IDs to async without sequence IDs means that the sequence IDs need to stick on the wall like a mosquito. You have to keep them somewhere. When you go back to like the egress of a system and you want to be reliable to the receiver, you need to introduce sequence IDs. So you need to sort of have a sequence ID generated that you sort of associate with that. But like we always do only one-step translations, which makes it really easy because you're doing like a Manhattan scheme. Like you're sort of like doing a Manhattan traversal of a grid of streets. Like you're only descending one level at a time. And so it's a very, you know, elegant way of sort of having at the very bottom in the engine something that's super close to Rx, like it's IQbservable with just this one level removed in the phasing, like it's you subscribe and then you have to start and you can visit it to give it schedulers and to stop it and to checkpoint it or to get debugging output or give it loggers. But other than that, like there's no change there. And then on top of that, you have all of the realities of cloud and device. And in fact, the device itself is also an IRP. So we can come from the cloud and talk to the device and say, install this expression tree on the device. Again, same thing, unbound parameters that will have something like GPS.
Nice.
And the device will know, oh, GPS, that means I need to subscribe to this observable. In fact, on the device, it's not checkpointed. The device actually has regular Rx for C++ observables. So there we simply bind to an observable, not to a subscribable.
So going back to the work that Aaron had done.
Exactly.
Initially.
Yeah.
That you guys, of course, built upon.
Exactly. Yeah.
Right on.
Yeah.
Right on.
And the only difference there is like, you know, on the device, it's done in native, it's in a background service on the device. The things we have there is like, you know, an expression tree evaluator that can take a .NET expression tree and evaluate it against the native engine. So like that's some kind of a, you know, additional thing layered on top of the work that Aaron has done actually. Yeah.
Right on.
Yeah.
Good, man. So I have to say, I mean, I came into this thinking that RX was sort of involved. You know, when Windows Phone 7 first came out, you guys were excited that it shipped on the ROM.
That's right, yeah.
But the system itself wasn't really using it. And it certainly didn't have a counterpart in the cloud. Now, it's pretty much really deeply integrated.
It's very deeply integrated. It's actually...
So right on,
This one is always resident in memory, actually. It's like the rules engine is part of a Windows background service on the device that's actually using the native evaluator. So like it's always there. It's powering Cortana for a whole bunch of scenarios.
Excellent. And it's powering the part of the cloud.
Yep. Mm-hmm.
And I think it's just really nice to see that sort of looks like a garden of duality.
It is actually, yeah. It's
and it's nice to see it sort of. We came at RX from the very beginning from a very theoretical approach.
Mm-hmm. Yep.
And that blew people's minds.
Mm-hmm. And in this case, it's like it's not purely duality, which is like switching things around here. It's also symmetry in this case. Like it's really about like having a whole set of parallel planes that if you look at them, they look exactly the same. The same four concepts: observables, observers, subjects, and subscriptions. In fact, there's another concept called subject factory, which is just like a cold subject that you can use to basically instantiate new subjects. That's used for the edges of the cloud. Like the data provider comes in, says like I want to provide some flight information, like an airliner or something. They invoke a subject factory to create one of their publication points, and then they talk to us. But like once you have those 4 or 5 concepts, they're basically symmetric everywhere. Like the APIs, the IRP is the same everywhere. So that's really everything about symmetry really that sort of added to this mix.
Right on. Well, it's always a pleasure to come and talk to you, man.
Yep.
And it's really, again, really nice to see RX powering Cortana, and I think the future's continually bright.
It's very bright.
Thanks for spending time, man.
Thanks for the time.
Cheers.